My student addressed me as Dr. Ho. So the talk that I'm going to, the mock lecture that I'm going to talk on is fantastic laws of our physical world and how to use them. Okay, so you probably have learned a lot of mathematics, in your secondary school, in your polytechnic, or in JC, and you take a lot of things for granted. Okay, actually, a lot of these things that you know are no less magical, okay, and mysterious than what you see in this show here. Okay, and today I'm wearing something like a piece of graph paper, actually, and it goes well with what I'm going to do. Okay, so to make the lesson more interactive, if you could, okay, please log on, okay, to this website. Okay, okay, not everyone can be David Beckham, so you could just type any first name. It doesn't have to be a real name. It doesn't have to be a real email address. No, you just agree and then you just click start. And after that, you just type in the session ID. Okay, and you see a question on your mobile phone. Okay, you just sign on and you answer this question on your mobile phone. You can participate live in this lesson. Okay, so just now Jiaorui mentioned the physics preparatory course for NS guys. It's also open for girls actually. So I will be teaching that course, but I would usually do it in my living room. I mean, okay, especially now with the COVID situation, usually there are hundreds of students. Okay, the physics and engineering students, there will be lots of students. So no, we can't do it in person. So we will have to rely on online technology, and then we'll be doing it on Zoom and so on. Okay. So okay, let's move on. Okay. So one of the things that you think about, when you do physics or actually any other discipline, it's time, actually. There are things that change with time. Okay, so of course you know about yourself, your weight, your height, and of course now the number of COVID infection. Okay, it changes. That number changes with time. Okay, so I'm going to invite you, okay, to actually think about some quantities that change with time. Okay, and in a short while, I'll get your response. Okay, so maybe just look at the responses for the first question. Okay, okay, let me just try to enlarge my screen, and let's see your responses. Okay, so we have someone from Malaysia. Okay, so you're a little out of this map. Okay, let me, oops. Okay, sorry, let me just, okay. Okay, I can't really enlarge this. Okay, so here we see the green dots. Okay, so you're all scattered over Singapore. Okay, so it's nice that we have this technology that you can be anywhere in Singapore and then yet we can still interact live. Okay, so thanks for those who have responded. So now I'm going to go on to the second question. Okay, I'm going to pose this to you and see if you've got something interesting that you can think about. Okay, quantities that change with time. Okay, it doesn't have to be a physics quantity. Okay, it can be something else. Okay, so I'll wait for like 20-30 seconds, and we'll take a look at your responses. Okay. So of course you are a tech guy. Maybe you think about electric field. Okay, that's a possible answer. You think about mass. You think about maybe velocity or acceleration, and so on, or temperature. And I've got very interesting answers here. Okay. Okay. I think we should just look at. Maybe we'll come over to my laptop and look at the answers that the participants have submitted. Okay, your mood. Okay. It's probably not easy to quantify your mood, your happiness, your IQ. Yeah. So hopefully you'll go up a lot. when you come to NTU. Okay, not only we try to teach you skills and content, no, we also make you think hard, and hopefully, no, your brain muscles will be very, very strong. Okay, by the time you leave NTU. Emotions, age, okay, weight. Okay, yes, yeah. So usually your weight before dinner and after dinner is different. So sometimes I weigh myself before I eat, just to know how much I can eat, okay? Okay, good. So we have lots of interesting answers. So now we're going to go on to something a little bit more serious, okay, but we'll start very gently, okay? So you would have seen this graph, okay, many times, in your career as a student. So this is X against T graph. So X can represent a lot of things. And here we have a straight line that passes through the origin, okay? And you probably still remember this, even though you've gone through NS, know that the gradient of a line is the change in the vertical coordinate divided by the change in the horizontal coordinate, right? Because you have to charge up a hill, right? So if the hill is very steep, the line has a very, very large gradient. Okay, so if the change in X is very large over a small delta T, now you have a very steep line. Okay, to make life a little bit more interesting, okay, you see more curves actually in the university. Okay, so if you have a curve, how do you get the gradient? So if you're interested to look at the gradient at a certain point, you mark out a point and you draw a tangent line just touching the curve at one point, and then you do this straight line, and again you draw the triangle, and then you work out the change in X divided by the change in T. Okay, so in the limit that is very, very small, the change in X is very small, now we write this as dx dt. So those of you who have learned differentiation, you probably recognize this symbol, but those of you who have not, don't worry, there is a course on calculus, when you join NTU, and you learn this, within one semester. Okay, but today we'll see how much, you can learn, okay, online. So now if I say dx dt, okay, which is the gradient, is equal to 5. Okay, how does the graph of X against T look? Okay, so it's going to be always the same value, so you'll be a straight line, right? And now if you look here, if X goes up by 20, T would have moved by 4, okay? So 20 divided by 4, that will give you 5. But it's possible to also have another line, okay, that has the same gradient, and you actually have a whole family, okay, of lines, okay, that corresponds to this. Okay, so maybe X is your salary, and T is your age, in future. Okay, maybe that's how it will look. Okay, so there is something that is constant, changing with time. Okay, so here we have another thing that is probably well known among students. You're going to drop if you drop something, you release something from rest, okay, it's going to experience gravity, constant. Okay, I'll just round it off to be 10 meters per second square. So if I release this, okay, you'll fall to the ground, okay, and it's going to go every 1 second it's in the air, okay, it's less than 1 second in the air, okay, it's going to gain 10 meters per second, okay, and so on. So the rate of change of velocity is a constant number, so we use the symbol v for velocity, so dv dt, okay, is equals to g, which is a constant number, okay, and now you get the equation of the straight line with an intercept. Now, I can throw it down, and my v naught will be a different value, okay, but I will get all these straight lines. Okay, so I'm going to push a little further, okay, because we can say velocity as the rate of change of position or rate of change of displacement, okay, and you can rearrange, you can further integrate this, okay, that's something in calculus, and then you get this familiar looking kinematic equation. Okay, so now I'm going to make things a little bit more interesting, hopefully. Okay, so I've added an x behind a constant. So dx dt, okay, is equals to 2x. So it means that the gradient now is going to vary with the value of x. The larger the x that I'll have, the steeper will be the graph. The smaller the value of x, the gentler will be the graph. Okay, so if x now is close to 0, okay, on the vertical axis, I'm going to get something that is quite level. Okay, but if the value of x is large, I'm going to get something steep. Okay, so can you think of function that behave this way? Okay, so for those of you who have learned calculus, okay, so this means that this, you differentiate something and you get back the same expression with a constant. Okay, and the only function that has this, okay, one of the function that has this behavior is the exponential function. Okay, so here if we look at this graph here, okay, this is your exponential graph. Okay, so if you look, okay, I'm not sure whether I can get a pointer. No, I can't. Okay, so if you look at the value x is equals to 20, the line is quite steep. You look at x equals to 1, okay, it's gone to the negative region in the t-axis. Okay, so if you just plot out, okay, the gradient at various values of x, you will get a curve such as this. Okay, and this is another possibility. There's a whole family of them. Okay, if I add a negative sign in front, the graph flips the other way, and here we have exponential decay. Okay, so we have exponential increase and exponential decay. So exponential decay is something that you see, okay, in radioactivity. So here, this is a cobalt-60 nucleus. Okay, so if you start off with 10 grams, okay, it's 100% to start. In one half-life, which is 5.27 years, the amount is expected to be reduced to about 5 grams. Okay, so this is a theoretical curve. Okay, but this mathematical equation describes it very well. Okay, and this is our exponential decay, and it's just this very simple relationship. You see this also in other topics in physics. Okay, so here I'm going to teach you something new. Okay, I'm going to show you this device, okay, that is known as a capacitor. Okay, so I'll probably need Michael to help me with the mic. So today I have this chair. So I think Michael alone should do the job. So Michael will now be my mic stand. Okay. Right. Michael the mic stand, okay. Okay. So the mic stand decided to stand on this side, okay. Okay, let me shift my chair. Okay, so on the slides, now you see two parallel plates and it's connected to a 12-volt battery. So when the plate is neutral and it's connected to a battery, okay, the positive end of the battery would draw electrons out of the plate. Okay, if you take electrons out of a neutral plate, okay, you'll be short of electrons and it will become positive. Okay, and you deposit electrons on the other side, so it becomes, you have too many electrons compared to the positive charges, so it becomes negative. Okay, so in this way, we can store charges. And the relationship between the charge that's stored on the capacitor and this quantity capacitance, the charge storing capability of the device, okay, is given as Q equals to C times V. So V is the voltage. So if I change it to a 24 volts battery, my V will be 24. Okay, and I will be able to store more charge, okay, for the same capacitor. Okay, so now I'm going to charge out a capacitor. Okay, so I'm going to store it with energy. It is a movable mic stand, okay. And now there is energy in the capacitor. Okay, now I'm going to discharge. Okay, so you see the glimmer of green light. Okay, the light is gone very quickly. Okay, so this is an evidence. Okay, so now there's very little energy that's left in the capacitor. Okay, so I'll just do this again in case you missed it. Oops. Okay. So you see that the energy from the capacitor is discharged across the LED light. Okay, there's a very interesting relationship. Okay, now with the capacitor, okay, when it's charged up and I discharge it across a resistor, okay, it follows this interesting relationship. Okay, dq dt. So Q is the amount of charge that's stored in the capacitor is equals to negative Q divided by the resistance of the resistor multiplied by the capacitance. Okay, And this is the equation that we've seen, right? Now, here in radioactive decay, the similar form, okay, but it is slightly different. Okay, and the graph that describes how Q varies with time now is also this exponential decay. Okay, and if you look at the half-life on the horizontal axis, it's the resistance times C. Okay, so now we're going to try something interesting. I'm going to charge up the capacitor. Okay, and I'm going to discharge it across a particular resistor. And you can witness exponential decay for yourself. So do you see that the brightness, okay, it gets dimmer and dimmer. Okay, and the brightness follows the exponential decay curve, okay, and varies with time with the exponential function. Okay, so now I'm going to discharge it over another resistor, and this resistor has a lower resistance. So you have a low resistance, you expect the half-life to be shorter, okay, and the graph to be steeper. Okay, so do you see the rapid reduction, okay, in the brightness? Okay, thank you, Michael. Okay. So I hope you have experienced for yourself, you witness exponential decay, okay, in real life. Okay, you can't see it in radioactive nuclei, but you can see it in a capacitor circuit. Okay, so the equation, okay, that you've seen is also applicable in first order chemical reaction. Okay, so if you have a high concentration, of a certain reactant, A, okay, the rate of reaction will be very high. Okay, and it decays exponentially. So here is an equation involving hydrogen peroxide. So at the beginning, when you have high concentration, okay, the reaction will be very fast. Okay, so now I'm going to do something more interesting. I'm going to modify the right-hand side of the equation a little bit more. Okay, we have that negative sign, negative 2x just now, but now I'm going to add a constant to it. So now it's 5 minus 2x is equal to dx dt. Okay, so if you just examine this equation a little, okay, you probably will realize, if you have x as 2.5, okay, it'll be 5 minus 2.2 times 2.5, and that will give you 0. Okay, and it looks like this graph here. Okay, and when x is equal to 0, okay, dx dt, the gradient is going to be 5. So it's going to change from a gradient of 5 at time t equals 0, okay, to a gradient of 0, okay, when x becomes 0. Okay, and the equation of this graph is given as x is equal to 5 over 2, 1 minus e to the power minus 2t. Okay, that's the equation of the green line, the blue line. Okay, and if I change from 5 to 3, I get a different line. Okay, so this is like flattening a curve, right? Okay, so this can happen also in charging a capacitor, or maybe you're eating your dinner. So when you're very hungry, your x is close to 0, is your maybe how full your stomach is. Okay, you eat very fast. Okay, but when you are close to full, you eat more slowly, so it tapers off. Okay. So this actually happened. This equation is also applied in analyzing, okay, free fall, okay, not in a vacuum, but in air. Okay, so when an object is moving through air, okay, the velocity will affect the air resistance. So in this case, okay, it's a constant b times v. So it means that the faster you move, the larger the v, okay, the larger will be the resistive force. So here, if you just release something through air, you have a constant minus vv equals to ma. Okay, so here, okay, we will see that this velocity, will not just go straight up, but the curve will flatten. Okay, I hope you can make the connection here. Okay, I didn't make my v red, okay, on the right-hand side, but I hope you can see the connection. Okay, you have a constant minus something times a variable, okay, which is like the equation that we have here. So you get the same type of graph. Okay, but if you have a larger object, okay, falling through air, you have to modify the equation, and it's proportional to velocity squared. Okay. So now let's take a look at a simulation here. Okay, so this is produced by a software called Console. Okay, so you have two objects with different shapes. So when it falls through the liquid, it gives, you can see how the position changes with time. Okay, so now we're going to look at a video. Okay, and you'll see this equation in action. Okay, and I'd like to have an opinion. Okay, watch carefully. Okay, I'm going to ask you to comment on whether you think this is possible later. Okay, so let's get the movie going. Okay, this is James Bond in 1995, I think. Okay, he's riding a bike, chasing a runaway plane. Okay, and this plane plunges off the cliff, and James Bond, knowing physics, decides to follow. Okay, and look at him. He's in a streamline shape. His hands are next to his body. He's going down, and here he spreads his arm a little bit more. Okay, and he catches up with the plane, moves at about the same speed, and grab, and he goes in. Okay. And as all good Hollywood movies, there is a good ending. Okay, so I'll leave you to watch the rest of GoldenEye for yourself. Okay, but I'm just going to pose a question to just ask your opinion on this. So do you think, James Bond will catch up with the plane? Just for fun. Okay, let's take a quick look at your responses. Okay, so do you think James Bond knows physics? Okay. Still thinking? Or you're watching the rest of the movie? Okay. Okay, maybe you don't have to write the reason. Maybe you can explain. Okay, yes. Okay, no, because the plane has higher terminal velocity than the person. Interesting. Okay. So what determines terminal velocity, or the magnitude of terminal velocity? Okay, I think probably you need to think about the shape and the weight. Yes, he's just an actor. Oh man. Okay, no, because he has less weight than the plane. Okay, so some of the factors of consideration are coming in. Yes, he's lighter and has less air resistance. Okay. Yes, since the air resistance on the plane is higher, coefficient of drag. Okay, good. So you're thinking. So it's fun, right? To think about physics when you're watching a movie. Okay. I mean, make sure you're with the correct company. When my wife watched movies with me and I comment about physics, she get pissed off. Yeah. Okay. No, he's too light and so on. Okay. So for the fun of it, okay, I did a simple simulation using this software called Algodo. Okay. So I'm going to have a plane, okay, flying off the cliff, okay, and a motorbike chasing after it. Okay, but this guy is not James Bond, and let's see what happens. Okay, so that's the plane off the cliff, and that's James Bond with James Bond's configuration, the motorbike. And you see, no, it's overtaking the plane. Oops, and you hit the ground. Okay. So he even overtake the plane. Okay, so this is a very simple simulation. Okay, done by one of my students, and he checked out the model of the plane and motorbike and so on. Okay, good. Okay, we're having a lot of responses. Okay. So actually, now if you watch carefully and you see that actually James Bond, okay, is actually catching up with the plane. Okay, the distance is getting shorter and shorter. There was no cut and paste in a certain scene. Okay, so I believe, if the cliff is tall enough, okay, he will probably catch up with the plane. Okay, so let's say indeed he did catch up with the plane as it was shown, okay, in the movie. And if this is how the velocity of the plane changes with time, okay, so now I want you to sketch how the velocity of James Bond changes with time. Okay. So maybe I'll hide the responses first. Okay. So you can actually draw with your finger, okay, on your mobile phone. Okay. How do you think, okay, the velocity of James Bond, okay, would vary with time? Okay, as he catches up the plane, as shown in the movie. Okay, let's do it as shown in the movie. Okay, how do you think the graph will look? Okay, let's take a look. Okay, let me just refresh. Okay, so this is the graphic. Okay, I got some answers. Okay, I got 3 responses. Okay, good. Okay, so this line is correct. It starts after the plane, okay, because it goes off the cliff slightly after James Bond. Okay, v is the vertical velocity. Okay, so here for this graph, okay, it needs to be a little after. James Bond didn't go to the edge at the same time as the plane. Okay, good. I think you can change your answers. Smiley face. Interesting. Okay. Okay, good consideration. Okay, but bear in mind, James Bond went off after the plane. Okay, so you have to start with the velocity a little after 0. I think you can actually modify your answer even though after you're submitted. Okay. Okay. Okay, good. So this graph has nice features. Okay, you start later than the plane, and now if you start later and you want to catch up with something in front, you have to move faster than the thing that's in front of you. Okay, so that feature is given in this graph. Now the blue line is larger than in value than the red line representing the velocity of the plane, right? Because you're from behind and you want to catch up and overtake, or just catch up. Okay, you will have to have a larger value. Okay, I got 1 correct answer. Okay, so you probably noticed that actually James Bond was changing the shape of his arms. Okay, he was actually trying to slow down, okay, as he gets closer to the door of the plane. Okay, so his air resistance actually increased. Okay, and he tried to match it in a way similar to the velocity of the plane so that he's of relative 0 velocity to the plane and he can just climb in easily. Okay, so this is what is happening. And you see the curve intersect a second time. This is when they have similar velocity. And this is probably the time that he gets in. Okay, and for those of you who still remember your physics, you know, the area under a velocity time graph gives you displacement. Okay, and now the area under the blue line has to be the same as the area under the red line. Okay, so good. So interesting responses. Okay. So next time you can put on your physics thinking hat. Okay, keep on thinking, just keep thinking about physics. Okay, and enjoy the movie. Okay, interesting answers. Okay, so let us move on to other things. Okay, so this is how now we can sketch the graph. Okay, so the curved red line, okay, will be James Bond. Okay, so at the beginning, James Bond puts his hands close to his body, okay, so that he has a low air resistance and he can overtake the plane. And after that, he has to spread out his arms to slow down, to catch up the plane, to get in. And the area under the 2 lines are the same, okay, because that's vertical displacement. Okay, so here we can look at other similar systems, and you see that the equations look very similar. Okay, so you just learn how to solve this first order differential equation. You can use it in cooling, resistor circuit, chemical reaction, radioactive decay, and biological systems. So it's actually very useful. So just now Prof. Chong was saying that physics is very versatile. So this is just a simple illustration, okay, of the versatility of physics. You can even use it in economics, okay? So simple message, more curves in uni, okay, but often you find common underlying principles. Okay, so recently, we talk about flattening the curve, okay, And if you go search papers related to COVID, you see differential equations. So now if you look at equation 1 again, you have ds dt equals negative beta si. So here you probably recognize, oh, this looks a little similar to the equation that we've just seen. But of course, there's one layer of complication because I is also a variable, okay, and it also varies with time in the second equation. Okay, but don't worry, you have 4 years to learn all these things. No hurry, we're just doing this very quickly in just like 20 minutes. And presumably you have learned quite a bit already. Okay, I hope it gets you excited. So there are also quantities that vary with space. Okay, so from this point onwards, I'll go a little faster. Okay, just to do the span of topics. Okay, so there are things that varies with space. For example, the height of buildings, the temperature in a room, the wind speed, and so on. Okay, so every point in space, the quantity is different. Okay, so an example here in 1 dimension, you have a light source. There's on an absorbent material. Okay, so if it's thick, less of it will get through. And here you see how the intensity changes with x. Okay, and here x now is not time, but here x is the thickness. Okay, so now we're going to go up to 3D. Okay, I'm going to bring you to Mount Everest. Okay, although I think there's some COVID cases there, but here we're just going there virtually. Okay, so here you see a contour plot of the height, okay, for Mount Everest. So just a very simple question for you. Okay, just looking at this contour plot and thinking of the meaning behind this contour plot. Okay, can you tell me which point is steeper? Is it point A or is it point B? Okay, so I'm going to deliver this on learning catalytics. Okay, so this is actually the beginning of learning vector calculus. Okay, I'm just letting you have a sneak preview, okay, of what you're going to learn in semester 2. Okay, you're going to learn calculus not just in 1 dimension, but 2 and 3 dimensions as well. Okay, so one of the things that you learn is the steepest descent. Okay, so now if you look at these 2 points A and B, okay, which point do you think is steeper? So one way you can think about it is, if you move a certain distance, how much do you fall? So every line that you cross here, okay, is 100 meters. So if the lines are very close to each other, okay, you just move a little bit, you fall a great vertical distance. So it will be steeper. Okay, so I think majority of you, okay, good. Okay, you selected B. So you're ready for second sem mathematics. Okay, you have the correct intuition and keep it that way. Okay, so there are also other quantities that varies with space. Okay, the temperature in the room. Okay, and airflow. Again, something very important now because of COVID. And you see this symbol, this inverted triangle, which strike a lot of fear in students. Okay, this is the derivative in 3D space. Okay, there are also quantities that varies in both space and time. Okay, so here you have a electromagnetic wave. Okay, so what is happening here is you have a changing electric field and it gives you a changing magnetic field and it gives you a changing electric field and it gives you a changing magnetic field. So this happens even in your mobile phone. There's actually a little antenna inside your mobile phone. So the charge is, if you jiggle the charge up and down at a very high frequency, okay, as long as it's oscillating, you produce this electromagnetic radiation. And there, you can actually communicate with your friends. Okay, so this is something that changes with time and space, okay, and that's electromagnetic wave. Okay, and there's a whole spectrum of them, okay, depending on the wavelength, but they all travel at the speed of light, 3 times 10 power 8 meters per second. So it means that 1 second, okay, if you travel at this speed, okay, you've gone around the Earth 7 times, okay, so 7.5 times, you want to be more precise. Okay, it's a huge velocity, so you can watch soccer matches live in UK, even though it's far away, okay, because you have all these signals. So more interestingly, if you take a certain gas, okay, in this case hydrogen, okay, now if you look at what's inside a hydrogen atom, now you have your proton and your electron, and you have discrete energy levels. So now when you go from excited state to the ground state, now it will give you a certain color of light. Okay, and every gas would have its distinct, I would call this barcode of light, and you can identify a gas that is even far, far away. Okay, so for example, how do you know there's hydrogen in the sun? And what are the elements present in distant star, even though you can't go there? Okay, so you can collect light from these faraway places and analyze the spectrum. Okay, you don't have to perform any chemistry experiments, right? So in this sense, physics is better than chemistry. Okay. So there's another thing that physics is better than chemistry. Okay, if you look at these quantum dots, okay, in chemistry, if you want to get different colors, okay, you need to try different compounds to get the color that you want. Okay, in physics, now you have this quantum dot. Okay, and this equation tells us that if I vary the size of the quantum dot, okay, I'm going to get different colors. Okay, so here you see the size and how it varies with the color. Okay, so the bigger the quantum dot, the longer will be the wavelength of the light emitted. Okay, and this is used in actually consumer technology. Okay, your iPhone, there's actually quantum dots in them. Okay, to give you your RGB. Okay, and of course, some TV also make use of quantum dots technology. Okay, and of course, in biology, you can use it as a cell tracker. Okay, so we have spoken about space, varying, things that varies with time and things that vary with space. So now you can look at space-time. Okay, so if I mention space-time, okay, if you're nerd enough, you think of relativity. Okay, and relativity, special relativity, you learn first. Okay, it's just based on two foundational rules. Okay, and they're not difficult to understand. Okay, the first is laws of nature are the same in all inertial frames. So if you're moving in a car with a velocity compared to someone who's stationary, the laws of physics in the car, and the person that's on the ground, stationary, will be the same if the car is moving at a constant velocity. Okay, and the speed of light, no matter who measures it in a vacuum, will always be the same value. Just based on these two very simple postulates or foundational rules, we can derive very exotic things such as length contraction, time dilation, and after a few pages of mathematics, you get E equals mc squared. Okay, so why do I say this thing? Okay, because in life, you will encounter a lot of other things that's not related to physics, but you also have this pattern of specific grounding rules, and you have to deduce all the implications. Okay, taking COVID situation as an example, my rule is everyone must wear masks. Okay, and you can derive all the consequences if everyone wears a mask, or everyone must get vaccinated. Okay, so what are the consequences? On the social, in the society, and on the businesses. Okay, so there is also a very important skill that you learn that's transferable to other areas of life. Okay, so I think this is probably a good point to end. So if you've got any questions, you could email me at this email address here. Okay, thank you for your attention.